Okay, so welcome, Niklas Boers. Thank you for talking here today. So Niklas is a professor at the TU in Munich. He did his PhD at the Humboldt University in Berlin in 2015 and has sort of collected several prestigious awards on the way. So amongst those, the Outstanding Early Career Scientist Award of the AGU, the NP section in 2021. And he works on extreme events and tipping points, early warning signs, and typically publishes in high impact journals. And we will see today, I guess, as well, quite a large variety of methods that he masters. So from network theory, dynamical systems theory, time series analysis, and recently also machine learning. And so he's going to talk today about tipping points in the climate system. And please, it's all yours. Thank you.
Thank you very much for the kind introduction, Georg. So I'm going to try to share my slides again. I hope you can see them, and I hope you can also see my cursor. Very nice. Okay. Yeah, so I'm not going to talk much about extreme events. I'm not going to talk much about networks. I'm going to focus on tipping points, or let's say critical transitions in the Earth's climate system, or in the Earth system, including its vegetated land surface. And this is joint work with Niels Bocho, Chris Boughton, and Martin Ripdahl. And I'm going to start a little bit, taking two steps back with this, what many of you probably have seen, but those who are not so familiar with the with climate science, I thought it might make sense to sort of give a little bit of background. So what you see here is the very smooth temperature evolution from 1950 to 2000 and roughly 15 in black. And you see for given different speculated emission scenarios and basically scenarios of how humans are going to emit greenhouse gases in the future until 2100, you see the corresponding global surface temperature change relative to the mean between 1850 and 1900. You see there's massive spread, but most of them increase. The light blue one is very hopeful scenario where we have an increase until 2050 and then a slight decrease. That would be great, fantastic, but it might also play out differently. Currently, sort of with what is implemented and what is promised, we will run towards something like almost 3 degrees by the end of the century. But it's very uncertain. Because you see by the shading, it's uncertain because we don't know what we are going to do as humans. It's also uncertain because even if we would know precisely, then the climate sensitivity, so the temperature response to the radiative forcing induced by the greenhouse gas emissions, is extremely uncertain. There's a range of a couple of degrees there. And then, of course, different models give different answers to this. But yeah, so what we know is the temperature is rising, the planet is warming, we know why. The corresponding global mean sea level rise, just as one important example of what the consequences of the warming are somewhere between 0.5 meter and 1 meter up to 2100. But this is all assuming that everything will behave gradually, basically that it's really just a linear, gradual, smooth response in the climate system to the changes in radiative forcing. There is not really a way with the current comprehensive Earth system models to do it differently, apart from what people call storyline approaches, saying, so what if an ice sheet like the Western Arctic ice sheet would destabilize within this 2100 years? And then you get very different global mean sea level curves here in the dashed line. These ice sheet models are typically not dynamically coupled into these models yet. It's ongoing research to do so. That's why it's not a standard, not the standard runs where you have these, and that's why the dashed line is sort of different. The sort of scary thing is that if we do this until 2300, then we might have up to 7 meters or even 15 meters of global sea level rise that cannot be ruled out. if ice sheets lose stability and basically collapse into the oceans. And this gives rise to this question, apart from the gradual smooth warming, and of course in geological timescales, what the warming isn't smooth, it's not gradual, it's very strong, it's stronger than it has probably ever been on a global level, at least in the last millions of years. But then still, if we look at the temperature curve, it looks rather gradual. The question is, could this trigger comparably abrupt responses in some subsystems of the Earth system, like the polar ice sheets in Greenland and Antarctica, or the Amazon rainforest? These are all examples that have been mentioned many times. And the question is, which of these, which subsystems in the Earth are there that could show such an abrupt response? Of course, the question is what kind of mechanisms would trigger that. And most of you have a background in dynamical system theory, of course, already think about bifurcations. That's also what comes to my mind when I hear this. Then, of course, the question is, what are the critical thresholds? What are the critical thresholds in the forcing levels, and what are the critical thresholds possibly in the rate of change? So even if there's no bifurcation, then the change could just be so fast that we could have a rate-induced transition. And then the question is, what are these critical values? And that is an extremely difficult question, because we have a very complex high-dimensional system at our hands, and then we don't really have models that reproduce the strongly nonlinear behavior that we observe. So we were going to try to work towards an answer, but I can already tell you I'm not going to give you an answer. Nobody can. From the IPCC, if you search in the summary for policymakers, what's there on these abrupt transitions, then you find these two quotes, that the abrupt responses and tipping points of the climate system, such as strongly increased Antarctic ice sheet melt and forest dieback, cannot be ruled out. And then there's this IPCC jargon that you say, they say this with high confidence. So with high confidence, they can't rule out that this will happen. And the second statement I found was the Atlantic meridional overturning circulation, which some of you might know under the name of the Gulf Stream, is very likely to weaken over the 21st century for all emission scenarios, even the light blue one that you saw. And there's medium confidence that there will not be an abrupt collapse before 2100. Now that's, again, I find this in a sense, it's a funny statement. There's only medium confidence that there is no abrupt collapse before 2100, which basically just says we don't really know. And yeah, so we're going to try to find out a little bit more today. This is a figure from a very recent paper, a perspective paper or review paper in Science, McKay et al., where they gathered the knowledge of, basically they made a literature search for the critical forcing levels. And this is what they came up with. So you see these burning ambers that give for the different tipping elements or different proposed subsystems of the Earth system that might exhibit abrupt transitions. You see the corresponding global warming levels relative to pre-industrial levels at which the tipping is expected. And the one important thing here is that this should not be misunderstood as a probability density function. There are these different colors, and then they also say something about possible or likely, but for none of these tipping elements do we have comprehensive and sufficient data or some simulation data to really derive probability densities. And in fact, if we had, then basically what these densities would represent would be the model spread. So we could have different models, and then the models would give us different outcomes at where the systems would tip in terms of global mean temperature. This ignores the fact that there's rate-induced effects, of course, that the speed at which the temperature changes might play a role. And it ignores the fact that all models could be wrong in the same way. So one should not misunderstand the model spread, the distribution that you get from an ensemble of model simulations, with the actual uncertainty that is related to this. So they could be biased, it could be off by 2 degrees or something like that. And this is just so really I mean, yes, it's important to sort of give a status quo on where this might be, but it's really also important to understand that this is this research is not done. We are just at the beginning of this.
Sorry, Niklas, can I just ask a brief question
Yes,
here?
please. Oh, yeah, I should say this. Please ask any time in between. Please interrupt me.
How did they come to those colors? How did they, measure or quantify those, likelihoods of tipping?
It's not a likelihood. That's what I.
No, but I mean, how do they say it's likely or very likely? That's what I mean. Yeah, I didn't mean likelihood in the.
Yeah, it's basically well, I mean, it really depends. Like for the Amazon rainforest, there's a couple of completely different model simulations with different models, different setups. And then one might say at 2 degrees warming, there could be a collapse. The other one might say 6 degrees. And then it's an expert judgment to say it's going to be at 3.5 degrees and likely range between 2 and 6. It really should not be misunderstood in terms of really quantitative estimates that are close to what we expect to be the reality.
Thank you.
Okay, so that's why that is the big question mark. Basically, this just tells us there's a lot of work to do. One could say, and there's many people who say this, and I have this sort of prejudice that the people who work with the very comprehensive models are overrepresented in that group, who say abrupt transitions that doesn't happen because it does not happen in their big models. Of course, I mean, this is provocative. Don't get me wrong. Just to convince people, there is a lot of evidence in the paleoclimate record that abrupt climate transitions have occurred in the past. And this is one example. It's a temperature record from Greenland for the past 120,000 years. It's not directly temperature, it's a water isotope in Dale 18O. And this shows the last glacial period, so the last, colloquially speaking, the last ice age. And you see these abrupt jumps, the Dansgaard-Oeschger events. For example, this one was 15 degrees, give or take, within a few decades. And I would say these are the archetype of abrupt transitions. And just in the last 6 or 7 years, have we managed to produce oscillations in comprehensive Earth system or climate models that resemble these. Doesn't mean we reproduce them for sure, but at least we have oscillations that give time series that look like the one that we have here. And this is basically, in addition to one other possible event, these are basically the only examples where abrupt climate transitions are reproduced in comprehensive models. Otherwise, they are too stable, too smooth. There's some other examples in the record, in the geological records on different time scales. So these are the jumps between ice ages and warm ages, of glacials and interglacials. These are on a time scale. This is 1 million years on a time scale, and this is to the corresponding. So what you see here is the global ice volume, basically as a proxy for temperature. But you also see how the Asian monsoon activity has varied in correspondence. So you also have these very abrupt jumps in the activity of the Asian monsoon over these 600,000 years. Of course, abrupt is always relative, but given the time scale, these are abrupt. That's the time series that we already looked at from this Greenland ice core, giving us the temperature reconstruction. And then more recently, during the Holocene, we have this North Atlantic ice drift which shows us abrupt, abrupt ice rafting events from the ice from the large glaciers, the last ice sheets on the northern hemisphere that were there from the last glacier mainly, the Fennoscandian and the Laurentide ice sheet. And you see these abrupt changes that are associated with corresponding changes in an Atlantic Ocean circulation. That is also very important for our climate that we're going to talk about in a bit. Yeah, so the question is, can we, if our models aren't in a good place to really do time series forecasting of these kind of trajectories, and they really are not, we might hope that in some years we have good reason to believe that we can sort of reconstruct the attractor structure or the dynamic landscape of these systems, but then still doing really forecasting on these timescales is just not going to work in the foreseeable future, unfortunately. But the question is, can we somehow do something else? Just using the time series that we have, using the observations, and plotting this very stylistic double-fold bifurcation diagram into this, just as some model, some very simple model for illustrative purposes to plot this. So most of you have seen this. So basically, we model the system in terms of the gradient of a double well potential for the drift and the additive white noise or Wiener process to mimic any sort of fluctuations, weather fluctuations that happen on this climate time scale. And the idea is that we drive this control parameter P from a situation where I have two stable states, and I drive this so that I'm losing the first stable state in which the system is in until I'm reaching the bifurcation point, and the system has to tip over to the other stable point, typically, of course, earlier than when the actual bifurcation point is reached because of the noise that drives the system and tips it over a little bit. And this is now the question is, how can we anticipate this? And there's a very well-known theory for this that all basically relies on the fact that if you compare this situation here with that situation, then we have a weakening of the restoring forces. Very visually, the boundaries of the potential well become less deep as we approach the bifurcation point, and this can all be formalized. What you have to do is you linearize around the given stable fixed point, then you discretize, which gives you an AR1 process, and this AR1 process has has known variance and autocorrelation given by these formula here. And now there's this parameter lambda, which we used which is basically when we linearize the dynamics. So this means we're fitting a quadratic potential around the fixed point, and then the lambda is this parameter here in front of the squared x. And what the lambda does, I defined this to be negative here, is to go from lower values, so more negative values, towards 0. And that is the reason why, as we approach the bifurcation point, the variance and the autocorrelation, the variance diverges and the autocorrelation goes towards 1. And this is really old news. Nothing is new here. This has been termed critical slowing down, this phenomenon. When the ecologists picked this up in the late 2000s, then they called this early warning signs or early warning signals. I do not really agree with that term because it's not necessarily an early warning. But what we see is that assuming that if the underlying assumptions are correct, then an increase in this negative lambda corresponding to an increase in variance and autocorrelation can be interpreted as a loss of stability of the given system state. Let's put it that way, that we can say. And of course, this works on a symplectic time series, as you can see here. And the question now is, what happens to the actual real-world tipping elements? And for all of them, we have some sort of observational data of different length. Also, they have different time scales. The Greenland ice sheet is extremely slow compared to the Amazon rainforest or the South American monsoon. And I'm going to focus on these 4 subsystems. Greenland ice sheet has about, and we're going to talk about that in detail, but what happens if the Greenland ice sheet melts, then there's fresh water that goes into the North Atlantic. The fresh water is lighter than salty water, so that makes the water masses lighter up there in this region. And that in turn reduces the sinking motion that happens there, which is basically the engine that drives an ocean circulation system that goes from the south to the north at the surface, and then the other way around at the bottom of the ocean, which is called the Atlantic Meridional Overturning Circulation, the AMOC, where the Gulf Stream is a part of. And so the melting of the Greenland ice sheet would weaken the AMOC. Since the 60s, thanks to work by Stommel, we know that the AMOC is bistable, so it has a strong mode, which is the one that we currently see, and has also weak mode, And as the Greenland ice sheet melts and the freshwater inflow into the North Atlantic increases, we are pushing the AMOC towards its critical point that might collapse to the really stable state. That in turn has massive a lot of impacts, including cooling of the northern hemisphere, warming of the southern hemisphere, and the southward shift of the intertropical convergence zone, which is basically the rainy belt around the equator of the Earth. And that would in turn then affect the monsoon systems of Asia, of Africa, and of South America. And in particular, in South America, there's two more bistable systems, strongly coupled bistable systems, namely the South American monsoon and the Amazon. And as we move down the ITCZ, that affects the Amazon, and it's currently not quite clear whether it affects it in a sort of positive stabilizing way or in a destabilizing way. Currently, we believe it would actually stabilize the Amazon, but for the monsoon systems of Africa and Asia, it would actually not mean a significant drying of those monsoon systems. But to first start with the Greenland ice sheet, this is reconstructions of the ice mass, usually given in terms of global mean sea level rise equivalent. The total melting of the Greenland ice sheet would be 7 meters. That will certainly take millennia, will really take a long time. It's a lot of ice that we need to melt. But I mean, even half a meter would be drastic, right? Because there would also be the additional contribution from Antarctica and so on. What we see here, so if you see the gray line here, that has been the evolution of the Greenland ice sheet in terms of global mean sea level rise. That's why it's going up, which means melting. You also see that there's incredibly large uncertainties around this. Basically, the uncertainties are as large as the signal almost. But what you see for the last 40 years, since 1980, where the measurements have become much more accurate, we see that we had a relatively quiet period during the first, from the 80s to the 2000s. And then we had a very strong increase in the melt rates and correspondingly a strong mass change since then. So basically this part here corresponds to this part in the left-hand side. Now, a lot of this is reconstructed using models. And of course, we want to sort of play this game where we don't want to trust the models at all, and we would just want to use observational data. So then we only have data since the 1990s, and that of course is not long enough to really trace changes in the fluctuations on the timescale that is relevant for the Greenland ice sheet. But this can guide us in a different way, because we can see that in this part here in central western Greenland, the so-called Jakobshavn-Isbrae glacier, the drainage basin, we have the strongest height reduction, so the strongest melt rates. And that was the reason why people drilled ice cores there. These 3 ice cores here at elevations between 2,000 and 2,500 meters, and one for comparison from a peninsula rather at lower elevation. And using these ice cores, they reconstructed the melt rates. And in addition, so that was this really direct empirical data of the melt rates for the last, let's say, 2 centuries. And then they also have a station here which has continuous temperature measurements since 1850 with the same instrument. So here we really have, there's a lot of the uncertainties that we typically have on these timescales in climate science. We don't have here. We have measured melt rates, and we have really measured continuous temperature record. The temperature record you see in blue, you see a model-based full Arctic temperature anomaly in red. They sort of agree, but we still know the blue one is more accurate. And we see the melt rates for this stack, so for basically an average over these 3 ice cores in blue, and for comparison on the peninsula in red. And what we see is that the temperature increase up there has been quite massive, more than the global mean. That's what people call the Arctic amplification. The Arctic warms faster than the global average. And the melt rate response seems to be nonlinear. It has almost not responded to the increase in temperature up to a point in the 1980s, which is when it has actually increased massively in terms of the mean, but also in terms of the fluctuations. Now, using these melt rates and reconstructing corresponding height changes in this region, just you start from a given level at the first time, and then you just sum up the melts for the melting for each year, and then you get a change in the height. We can make this put this into relation with a simple model of the height changes of an ice sheet, which is really very simple. It is this funny exponent 8, which comes from Glen's flow law, flow law. So this is derived from fundamental glacier physics, not by me, but by Anders and Ricarda, Anders Levermann and Ricarda Winkelmann. The key feedbacks that are relevant for the Greenland ice sheet, which again operate at different timescales, are the melt elevation feedback, where as the ice sheet surface is exposed to melts down, it reduces in height, and then because of the atmospheric lapse rate, it's just immediately exposed to higher temperatures, which gives us a positive feedback. Also, the albedo, as we melt away the uppermost layers, which are really white in snow, and it's basically snow, and then we expose the gray ice that absorbs more energy. So that's also positive feedback. There's snow line migration feedbacks, and there's the thinning of the outlet glaciers, which basically work as plugs for the ice that is on top of them. And as those melt, then we accelerate the ice flow into the ocean. There's also negative feedbacks related to the precipitation temperature feedback. So in a warming world, there will be more precipitation, so also more snowfall. There will be changing circulation as the height decreases. Basically, you allow more moist air to go across the ice sheet and deposit more snowfall, basically. And in a balance, as long as there's a balance between these positive and negative feedbacks, we will have a stable state, which I plotted here for relatively low surface temperatures. This is the potential in colors. It's the potential corresponding to this model. And we see the evolution of the Greenland ice sheet from those reconstructed height changes in thick red. We see corresponding comprehensive coupled model simulations in thin red, and we see the simulations of the simple model in the thin blue curves. So this all fits very well. Here locally in the central western Greenland part, it appears that we have already crossed the critical point, the threshold point, where the system gets out of balance, and then we expect even much more accelerated melt rates. But that's, of course, one should not take that for granted, because we're making a lot of assumptions. We're reducing a part of an ice sheet to a zero-dimensional system, and of course this might not be entirely correct, so one should not overinterpret this, but one might look at the fluctuations around this fixed point here to see if we actually see signs of critical slowing down that would support the hypothesis that there's actually instability loss associated with the increasing melt rates. Now, one other thing, just as a brief remark, just increasing autocorrelation and variance, or the increasing lambda, could arise for many different reasons. It's a purely statistical thing, and we want to relate that to mechanistic mechanisms. And to do so, we observe that for any model that has this form, which is basically a nonlinear f, just needs to be linear in the control parameter. For a fixed point where the f of x star is just AP, we can just do the derivative of the chain rule to find this expression here. So the sensitivity of the model, which is the change of the fixed point with respect to the control parameter, is given by A over the derivative as at the fixed point. And then on the other hand, taking the model again and linearizing around the fixed point and looking at the fluctuations, and then observing that lambda is nothing else but the f prime, then we can put in for f prime, we can put in lambda there, and we can, from this classic equation for the variance, for the fluctuations of the discretized time series, we can then get this equation, which shows that the fluctuations are actually proportional to the sensitivity. So if we have a model from which we can compute the sensitivity, and on the other hand, we have the fluctuations from the observations, and if this proportionality holds, then it's a good model. It's not we can't prove it's the true model, but it's at least not a bad one. If this proportionality does not hold, we can throw that model away. That is at least a way to sort of select out bad models from not so bad, or maybe even good models. And the similar expression you can get for the autocorrelation. Now doing this, if you look at this model here, it's the ice sheet model that I showed you before, but I removed the nonlinear terms. So the question is, can we explain the increase in variance that we see here? So the black is from the observations for the variance and the autocorrelations. Can we explain this increase with a model where we don't have a nonlinear term, which would sort of be the same as assuming that it would come from the temperature forces. So sort of the atmosphere would induce the increase in the variance and the autocorrelation, which is sort of the counter hypothesis to the actual stability loss of the Greenland ice sheet. And the answer is, if we look at the sensitivity of that model, of course, we don't see an increase in sensitivity because it is linear. The bifurcation diagram, it's not even about the stability diagram, it's just a linear line. And so the sensitivity does not increase, and then this formula for the autocorrelation does not increase. But in the observations, we see this very clear increase in the variance and a more moderate, but still significant increase in the autocorrelation, which does not agree with a linear model. So this just rules out a linear response, basically. And on the other hand, if we use the real model from the literature with the exponent of 8, then we get a very good agreement between the observations and the sort of the hypothesized sensitivity of the model for both the variance and the autocorrelation, which of course not a proof, but it's telling us that the model is consistent with the observations, and the observations tell us that the stability loss is going on in this part of Greenland. So that's so much for the Greenland ice sheet. We may have much stronger melt rates in the future, which will affect the AMOC. But before we go to the AMOC, the Atlantic Nodonal Overturning Circulation, let me make another remark. I already said this before when I came to the first remark. Variance and autocorrelation can go up for many reasons. And one, which is probably happening a lot, is that not the drift of our system changes, but actually just the autocorrelation and or the variance of the driving noise. And to sort of rule out that gives us spurious early warning signals, basically false alarms, the idea is to, instead of looking at the variance and the autocorrelation, find an estimate for the restoring rate lambda directly, maybe by regression. Of course, this would handle increases in the noise. It would not handle increases in the variance of the noise. It would not handle increases in the correlations of the noise. So now the noise isn't white anymore. But what we can do is we can fit, with using generalized least squares, we can fit a model that assumes autocorrelated noise, where we leave the AR1 parameter free, and fit both things at the same time. And then indeed, what you see here on the right-hand side is a linear model where I just ramp up the autocorrelation of the driving noise. So you see this actually also increases the fluctuations, but it also increases, so that's what you see in the increasing variance, but it also increases the autocorrelation. But nothing is going, there's no stability loss going on. So this is a perfect false alarm, beautiful early warning signals, but nothing is happening. And indeed, if you estimate this lambda correctly, then you don't get an increase, which is what you want to have. And still, obviously, if you do this on a system that actually tips, then still you get what you want. You get an increase in this correct lambda estimate. So now this we're going to throw at the AMOC. The question is, what is the AMOC? So this is a sketch. It's not, it tells you what the AMOC does. It brings surface waters. There's a whole Pacific MOC as well, but let's just look at the AMOC. There's water masses going from south to north, reaching this region here where they start sinking, because it's water masses that come there. When they come there, they were still warm, very salty. Then they cool down. So you have cold, salty water, which is heavier than the surrounding water masses. That's where they sink down. And that's the engine. that drives the circulation, and the water masses are then restored southward at the bottom of the ocean. And there's basically a salt advection feedback. So the more salt is brought up north, the heavier the water masses will be there, the more sinking, and that's a positive feedback. And that induces a bistability of the system. And I should note that in some models, like CMIP 4, CMIP 5, like early 2000s, some comprehensive models and most models, the AMOC was not bistable or appeared to be monostable, but that is really more of a problem with the models than with our understanding of the AMOC. I'm very convinced that this is actually a bistable system. Also from the paleoclimate evidence, you saw these Danskar-Oeschger events. I didn't really go into explanations there, but they are strong. I mean, it's very difficult to explain these Danskar-Oeschger oscillations if the AMOC were not bistable. It is not exactly the same as the Gulf Stream, although that's how it looks in the media. The Gulf Stream itself is a wind-driven system. Basically, so you have the trade winds going from, due to the Coriolis force, because of the rotation of the Earth, you have the trade winds and you have the westerlies, and basically in between they induce this huge gyre, and the Gulf Stream is the western boundary current of that. So, which is basically, it's this part here, and basically you can say as long as the Earth keeps rotating, as long as the Earth turns, there will be a Gulf Stream. It will not collapse. But the North Atlantic current, which is the extension of the Gulf Stream into the North Atlantic realm, and all that is part of the AMOC. This is density driven, as I explained earlier, about the relative weight of the water masses. And this indeed can collapse and can change just to a weak state. This is reconstructions for the past 1500 years using a lot of different temperature reconstructions, temperatures and other ways to estimate the speed of the AMOC. And you see that they all agree that the AMOC has weakened in the sense of it is less strong. It has not, I mean, we don't know if it has lost stability yet from this plot. We just know the circulation speed, so to speak, has reduced. And that reduction has started definitely before the Industrial Revolution. Of course, we cannot rule out that it's still sort of due to anthropogenic influence. We started deforesting the planet a long time before we started the Industrial Revolution, and that had impacts on the planet. But that's really an open question, whether this is a natural fluctuation or anthropogenic or a mixture, to which proportions, it's really unclear. The fact is just the AMOC has been weakening, and if we enforce in models, if we enforce a collapse of the AMOC, then there has been two example cases, one by Tim Lent and one by Chris Bolton, where they showed that the eventual collapse of the AMOC is indeed preceded by increases in the variance and the autocorrelation. So it looks like these are not the most comprehensive models, but they are complex enough to make it difficult to really find the manifold on which you could really say, okay, this is a double fold bifurcation or something like that. But still, just from the time series, you have this suggestion that these simple local stability concepts make sense, and then you have this increase in the indicators, assuming, so it's telling us that it makes sense to also look at this in the observations. The problem is the observations for the AMOC are only 30 years long. It's basically just, I mean, it's a little bit of a straight line with a slight negative trend. And we need something else. There is a very interesting observation from models that the strength of the AMOC, which in models, of course, you can measure arbitrarily long, so I mean, as long as you run the simulations. And in those simulations, the strength of the AMOC is correlated to certain patterns in the sea surface temperatures and the salinity of the Atlantic Ocean. And that is very handy, because then we can use those patterns to derive so-called fingerprints of the strength of the AMOC. And the sea surface temperatures we have since the 1870s, the salinity we have since the 1900s. And from there's a lot of literature in this, and there's a lot of fingerprints that have been proposed. And I'm just gonna use the theory and apply that to many of those fingerprints. I mean, 8, I think four sea surface temperature based ones and 4 salinity based ones to see whether there is something is coming out of that. But first, I'm just gonna look at the lambda pointwise, grid cell-wise for each point in the Atlantic Ocean. And on the left-hand side, I do this for the sea surface temperatures. On the right-hand side, I do it for the lambda. And so you see for the sea surface temperatures, basically the entire Northern Atlantic Ocean shows significant increases in the restoring and in the negative restoring rate, meaning a stability loss. And for the salinity, we actually see this, as I explained to you earlier. So here is where the North Atlantic drift sort of extends the Gulf Stream and brings the water masses up to the North Atlantic. And it's exactly this pathway of the North Atlantic drift, including this counterclockwise bending before it reaches the UK and then towards Iceland and south of Greenland. That's where we see the stability loss in the salinity-based data. And then looking at this via the fingerprints, which are all based on taking different regions of the Atlantic, normalizing this with respect to a large-scale average, to reflect that, for example, sea surface temperatures, and it's warming everywhere. What you see here is that it's not warming south of Greenland, which is exactly this thing. I mean, that's the main visual fingerprint of the weakening, because there's less heat brought to the North Atlantic because the AMOC is slower. And similarly, you see this spot here south of Greenland where there's also less, where the salinity is less, or the salinity trends are positive almost everywhere else. So looking at those fingerprints, we see quite clearly that the restoring rate lambda has been approaching 0 during the last 100, 200, 140 years. I should have stopped the dashed lines right where this is, because this led some people to think that it's okay to do an extrapolation into the future here. So what I don't mean is that this will hit 0 at a certain point in time. Please don't misunderstand me here. This is not what should be done. We're looking at past data. We're looking at historical reconstructions. All we can say is in the course of the last century, stability has declined. We have no idea what happens in the future. We have come closer to the critical threshold, but now the question where that critical threshold might be, we cannot answer using this whole theory. Plotting the same thing as a function of the global mean temperatures, just assuming that that is some sort of a control parameter, then we see that the variance increases exactly how the sensitivity of the Stommel-Sessi model would suggest to us. And so this basically tells us the AMOC stability, whether it's already in response to the increased melt rates from Greenland is unclear. But this is the take-home message from here. Now, as a last example, I'm going to change to land surface processes, which has very much less time coverage. Satellites haven't been up there for a long time, and that's the only sort of homogeneous way to measure processes at the land surface, vegetation processes. But the beauty of it is, they basically observe the entire surface of the Earth. So we have a lot of different time series, although not too long time series. And since we have a lot of places, we also have places where there have been abrupt transitions in the observed time series. So this is a vegetation optical depth index. So really, a forest has high values, a savanna has low values. And what we see here are these abrupt transitions induced by fires, where we can then just fit an exponential or fit a linear to the logarithm to really get empirically the restoring rate of that system, the rate at which it recovers. And that is sort of the classical definition in ecology of resilience, is the ability of a system to recover from external perturbations. And the question is, of course, is this empirically fitted restoring rate R, is that somehow related to that lambda that we can estimate, that we have spoken about so far? And if they are indeed related, then we basically have a empirical proof, we have empirical evidence that what we have been doing before is actually okay, because then we would know that the resilience would actually be reflected by this restoring rate. And So the problem, of course, if we would just do this fitting, then this was a time series where this happened 2 times in a row. That's very rare. And so sort of continuous changes in time, you cannot measure in this way. And also, if you look at how few points actually have colors here, that's the ones where we found abrupt transitions that were useful to estimate this recovery rate. And so that's a very coarse coverage of space, and we would like to have more. So what we did here now is we took this empirical recovery rate on the x-axis and just basically do a scatter plot, where we, for each time series, we compute the autocorrelation for the entire time series and the variance for the entire time series. And then what you see here is we do this for everywhere on the planet where we have colors here, where we could estimate the empirical recovery rates. And then in green, you see the theoretical expectation from that Ornstein-Uhlenbeck theory. So these are the 2 formulas. This is actually wrong. This should just be sigma square over 2 lambda with a minus sign. So what we see is that, in particular for the variance, the theoretical curve, the green one, is actually a very good agreement with what we get from the observations. So the autocorrelation is an offset. It's still a monotonic relationship, but one has to be a little bit careful at this point here. But then still, we would conclude from this that for land surface processes, vegetation, it's okay, sort of okay, to use the natural variability, really compute the variance and the autocorrelation, do that in sliding windows to look at changes, to estimate the response to the recovery from large perturbations, and hence to quantify the resilience of the system. And then, of course, so this is the plot from before with a very sparse spatial coverage. And what we see is how nicely we can fill all of space, basically, as soon as we just do this based on the autocorrelation and the variance. And then here we see where we have significantly positive changes in the variance and the autocorrelation. And one thing that I don't want to go into too much detail here, just the Amazon basin you see pops up very clearly. And indeed, the Amazon is suggested to be a bistable system with a rainforest state and a savanna state. And then there's different reasons why it might tip from the one to the other. One is just precipitation changes, but also deforestation, as you will see in a second. And indeed, we see for the vegetation optical depth of the Amazon, we see an increase in the 3 indicators, meaning the Amazon has been losing resilience, let's say, since some point in the 2000s, maybe 2005 or 2008, maybe earlier, depends on the data. And this loss of resilience has been stronger in drier regions, which is probably expected, but it's also stronger in regions close to human activity. So there seems to be a statistical suggestion that humans have something to do with this. And indeed, so what we did here was to come up with a simple model of the moisture budget in the coupled South American monsoon and the Amazon rainforest system, which they exchange a lot of moisture. Basically, it rains down from the atmosphere to the soil, and then the trees transpirate a lot of water back into the atmosphere. It's being picked up by the trade winds and brought further inland. And crucially, there's a positive feedback because there's a lot of rainfall here, a lot of convection, meaning a lot of latent heating. So that basically air masses rise because they heat up, and that creates, relatively to the Atlantic Ocean, a low pressure system. So amplifies the pressure gradient. And that's how you get a positive feedback that basically gives you the monsoon climate of South America. And then as you deforest, and we modeled this in just in a one-dimensional way from box 1 to 100, we just reduce the evaporation and the surface energy budget. And as you do so, then what you get is, so this is the direction and time, and this is the number of deforested boxes. And as you do so, we're reducing the precipitation first gradually in the westernmost box until the positive feedback collapsed, and we have an abrupt transition towards a basically monsoon off state, which of course then brings along the Amazon vegetation will respond to this, and then we will have a dieback of the Amazon because we have drastically reduced the precipitation. Now that's in the model, but we can use this model. Of course, it's again, so I mean, it's a sort of bifurcation that happens there. We see critical slowing down, and then we can use the model to guide us where to look for this, for signs of such a stability loss in the observations. And indeed, we see critical slowing down also in the monthly rainfall rates along the pathway of the moisture transport. We also see other sort of from the simulations, we could identify signs of stability loss that are not associated with this critical slowing down, but where basically what happens is the more you reduce the moisture in the overall system, the harder you make it to kick on this positive feedback related to latent heating, meaning your monsoon onset will become later. This is exactly what you see in the observations. The dry season becomes longer due to a later onset of the monsoon, and also this is what we see here, and also the soil moisture in vast parts of South America, in particular in the downstream regions, the soil moisture is decreasing, meaning we're basically sort of emptying the system gradually, and that's a precursor signal for a possible abrupt transition. So to conclude, and sorry, I think I took a little bit more time than I planned, like 5 minutes. To conclude, so we know that critical transitions that are induced by bifurcations are preceded by characteristic statistical changes related to critical slowing down. That's the term we use for that. And then we looked at the Greenland ice sheet, the Atlantic meridional overturning circulation, the Amazon and South American monsoon, and saw that for all of them, we do see evidence from the empirical time series. We do see evidence that there is a stability loss going on. But of course, this has all been based on on a lot of simplifying assumptions. Basically, we treated the Greenland ice sheet like an ice cube, which is a little bit of a simplification. And so we need more observational data. And we need better methods to basically bring together what we know from observations and what we know from models to constrain our model simulations more accurately. Thank you very much.
Well, thank you very much, Niklas. That was a fantastic talk. Very, very interesting. Quite scary if you look at the data. Are there questions? Yeah, Jan, would you like to unmute yourself?
Yeah, I have a question because, I mean, first, thanks for the talk. It was very interesting. My question would be, I mean, you're looking at spatial systems, so Greenland, for instance, and the Amazon rainforest. And in the one case, you show one time series essentially for the Greenland ice sheet. And is it that in this case, you just basically mask let's say the spatial extent of the glacier you're looking at and get the time series of that? And I mean, apparently the approach for the rainforest is a bit different, right? You get a time series per point, as far as I gather. And yeah. So, I mean, what motivates the different approach? And maybe also, do you expect anything from also looking at spatial correlation, which you don't do for now, right?
Yeah, thank you very much. Obviously, a very good question. So the short answer is we do what we can. For the Greenland ice sheet, if you want to have time series that are long enough so that you can at least hope that you're covering the timescale, the response timescales of the ice sheet, then you need at least, I mean, this is the longest that you can get, which is sort of 170 years or something. If you would use the spatially extended data, then you would have to start at 1992, so you have no chance in estimating fluctuations of the right timescales. Obviously, it would be extremely interesting to have these for 200 years or so and look at the spatial correlations. Also because of, you know, the changes in the surface mass balance and how they interact and so on. That would be extremely interesting. So we have to restrict ourselves to the central western part for now, because that's where we have these icebergs. For the Amazon, the response time scale is much faster. So it's okay that we have shorter time series that only cover, that only start in the 1990s, I think, yeah. So we have basically 30 years of data. And what Chris mainly did here was indeed looking pointwise at the single grid cells. But we have ongoing work where we trying to compare this with the spatial correlations, because for a vegetation system like this is in particular coupled spatially through the interactions with the atmosphere. It makes perfect sense to look at the changes in spatial correlations, which are in a sense related to the changes in the spatial variability of the system. Although the theory isn't, I mean, it's a little bit more complicated, and I don't think it is as robust to say that spatial correlation increase is a sign for stability loss as it is for if you do this pointwise.
Thanks a lot.
Thomas.
Niklas, talking about the data, especially when you are working in the paleo setting, obviously your time resolution will be quite low. That will affect your autocorrelation and the variance
Absolutely.
divergence, or?
Yeah, totally. Obviously, I mean, with paleo records, it's really complicated. I'm not sure. Sorry, I didn't mean to interrupt you.
No, go on.
Yeah. I mean, this is not just true for paleo records. And it is something that is, so the impacts of sort of non-stationarities in the data that do not come from the actual underlying physics, but from the way how the data are aggregated. That is something that is really very important to take care of. It's very obvious in the paleoclimate context that this plays a role. For example, I didn't show you, but for these Danskard-Oeschger events, let me see if I have a backup slide for this. No, I don't. For the Danskard-Oeschger events, you can find early warning signals prior to most of them, or let's say prior to a significantly large number of them, when you use these ice sheet reconstructions, which are, when they say quasi-annually. So what you do there is you count annual layers. You see the sort of seasonal cycle in the snowfall patterns, you see that, and you can count annual layers. And if you take thin enough slices from the ice core, you actually, let's say for the first couple of tens of thousands of years, you have annual resolution data. So that is fine. Of course, as you go further down the ice core, further back in time, then things become thinner and thinner, and then it becomes more difficult. But at a resolution of 5 years, it was still quite, and sort of taking into account the uncertainties and so on, it was quite clear that you could still identify an increase in the variance and the autocorrelation. Not directly, but using a wavelet analysis and then looking at the Hurst exponent and the wavelet fluctuation levels, but that would still be sort of an equivalent study. For example, for the, so here, for example, with the vegetation optical depth, this is a time series of 30 years, which is an aggregated time series where they merged signals from different sensors, which have different signal to noise ratios, which can then, of course, induce all kinds of changes in the variance and the autocorrelation with no change in the underlying system. So that is something you have to be very careful about. Also for the AMOC, these fingerprints, so it really depends on how the, salinity for the upper 300 meters of the ocean in the early 1900s, how are you going to measure that? I mean, it's just not really many direct ways. There's some measurements, and then it's really an analysis product. So there's, you use the whole Bayesian machinery and filtering machinery to produce data. But of course, there's massive uncertainties, and then you have to take those uncertainties into account to make sure that what you see isn't just the result of increasing data coverage. For example, with the salinity data, whenever there's really truly missing values in a given month, in a given grid cell, then there is the correction is that the climatology plus 90% of the anomaly of the previous month is filled in. And now that directly on the monthly timescale induces you an autocorrelation of 0.9. If you had no observations otherwise, but you just fill in that background information from the climatology plus these, then then you have subsequently no observations, then you're just inducing a 0.9 autocorrelation. That again, you have to, of course, you have to know that, you have to know how the data are produced, and you have to know how to take care of that. Absolutely.
Yeah, but that makes sense what you're saying about the 5 years for the ice core, because I'm currently playing with a student using your techniques on an ice core from Antarctica. And I was actually surprised how many big events I can still see in that ice core data, given that well, resolution is quite high on that ice core data. So yeah. But maybe we should.
In Antarctica, it's even better because you had higher
exactly.
accumulation rates, and then exactly.
Yeah.
Maybe I can ask a quick question. It seemed to me, I'm not sure I got that right, but that that the variance was typically, fit quite well by your, your predictions, whereas the autocorrelation function sort of was a bit iffy. Is that because it's harder to calculate the autocorrelation function, like with limited data, or can you comment on that?
It's a very good question. I don't know the answer. It might be what you. It might be that. It might also be that it's just more sensitive to measurement noise. But it might also be that the approximation of the variance is just that it works. That it just works better. Because we're anyways making this assumption that the system can be looked at as basically as an Ornstein-Uhlenbeck process. Yeah. And maybe the approximation of the variance is sort of more general than the one for the autocorrelation. We're sort of trying to understand this, and we have different hypotheses, but we don't know.
So there may be actually another model that is more suited for this. So what you're suggesting?
There most likely is. If you have an idea, please let us know.
Are there more questions? Well, if not, let's thank Niklas again for a really fantastic, great talk. Thank you so much, Niklas. Thank you.
Thank you very much for having me.